In this video, we're going to do another ice table problem. This time, we're going to have to find the equilibrium molarities. So let's take a look at this one here. Determine the equilibrium molarity of all species when 0.3 molar of H2 and 0.3 molar of Cl2 are placed in a vessel at high temperature and the following equilibrium is established. So the first thing we need to do is, if we want to find equilibrium concentrations, we need to make an ice table. So we'll have our H2 gas plus Cl2 gas produces some HCl, 2HCl. Now we have our K value given to us. That's going to be important later. So this is our ice table being set up. This will be molarity, I, C, and E. And here we have 0.300 molar. Here we have 0.300 molar as well. We don't have to put the molar in there because we put the unit off to the side there already. And then our product started off as 0. And our change will be based on the molar coefficients over here. So this will be minus x since it's consumed as a reactant, same thing here. And this will be plus 2x because it's produced as a product. And so now we're going to write out what our equilibrium concentrations are. And that. Okay, so there we have our equilibrium concentrations given to us. We need to find what the actual concentrations are, not just what the expressions are for them. So in other words, we need to go and find this x value over here. And once we have that x value, then we can go and plug them in to find the individual equilibrium concentrations for each one of these chemicals when equilibrium has been reached. So our first step anyways is to write out the ice table. Our second step is to make an equilibrium expression. So K is equal to HCl squared over H2 times I2. And now we can go plug in all the information we have. We have K, and we have these expressions here that we can plug into our K expression. So 870 is equal to 2x squared over 0.300 minus x, that's the H2, and then times 0.300 minus x, that's the Cl2. Now, we have to solve for x here, and so this looks pretty scary. It looks like we're going to have to bring this over to that side, distribute everything, expand, and then maybe use a quadratic formula if we can't factor. It looks kind of scary that way, but we can do something simpler. We have a nice situation here where we have squared on top and also squared at the bottom. So it looks like this. 2x squared over, because these are the same bracket, same contents, you can do 0.300 minus x squared. And now we can take square roots of both sides. Because this and this are both squared, top and bottom, we can do square root of this entire thing. And same thing over here. And so what we'll get is square root of 870 is equal to 2x over 0.300 minus x. And now I can send everything to the other side, distribute, and then solve for x. So it's as simple as that. So let's go ahead and do that. So let's send this to the other side, and it becomes square root of 870 times 0.300 minus x is equal to 2x. And I'm going to leave square root of 870 written like that, just so I don't have to have a whole bunch of decimal places right now. So I'll distribute this in here and in here, and I'll get square root of 870 times 0.300 minus square root of 870x is equal to 2x. And I'll send this over to the other side, and I'll get 0.300 times square root of 870 is equal to 2x minus square root of 870x. And I get, so now I'm going to actually plug my values in. So 0.300 times square root of 870 I get 8.848728722 is equal to 2 minus square root of 870. Let me try that one more time. This should be a plus. That's where I made a mistake there. Notice I saw I was going to have a negative x value, and that would not work. So as soon as I saw that mistake, I knew I made a mistake somewhere. And so I went back and I said, oh, yeah, look, this should be a plus here since I sent this over to the other side. That should become a plus. So I forgot to do that, and you might have noticed that before me, so that's good. So 31.49576.241x. And I can divide both sides by this to get the value of x. And so I get x is equal to 8.84872.8722 divided by that 31, 0.280949818. This is the x value. That is not the concentration of each of those. I have to go plug that x value into each of those. So step 4, the concentration of H2, which is also equal to the concentration of Cl2, is equal to 0.300 minus x. And remember that x is equal to 0.280949818. So we can plug that in there, and we get 0.019050181 molar, because it's a concentration, or approximately to 3 sig figs, 0.0191 molar. That's for both the H2 and the Cl2. So now we can take the same approach, but for the HCl, and we know that that's equal to 2x, which is equal to, so we can just plug in that x value into our x portion there. We get 0.561899636 molar, or approximately 0.562 molar. And there we have our equilibrium concentrations of all species once equilibrium has been reached. You can double check your work. So this is an extra step. Checking work. You can plug in the concentrations that you found into the equilibrium expression. And if you get the equilibrium expression, the equilibrium constant that you were given in the question, 870, then it means you did things correctly. So let's see if this actually works out. Plug in the unrounded values so you can get as close as possible if you're correct. So 0.561899636 squared over, I'm going to write this in there twice, so I can just write it squared since it's the same thing. And we get about 870. So that means that these concentrations are correct. So in this question, we had to find the equilibrium concentrations of the different species in the reaction. We were given initial concentrations and 0 for the product. We had to find some expressions to represent the equilibrium concentrations at equilibrium. We were given a K value. So we had to find basically this little X value over here. To do that, we had to make an equilibrium expression, plug in all our expressions with the variables, and then solve for X. Then we saw an easy technique to do that, so we wouldn't have to use a quadratic formula. Once we solved for X, we took the X value that we determined here, and we plugged it into the concentration at equilibrium expressions with the variable in there to figure out what the new concentration was. And then we rounded to the correct number of sig figs, so 3 sig figs each. We checked our work by basically plugging in our equilibrium concentrations into the equilibrium expression to see if it matched the K value provided to us in the question, and it did. And that's essentially what you have to do when you want to find the equilibrium concentrations given the equilibrium expression. There are situations where you won't be able to solve for X this easily, and you might have to use a quadratic formula, but that you'll see in the next lesson.